Today we are going to use Abaqus to model the beam shown here. The Young modulus of the beam is 200 gigapascal and its Poisson's ratio is 0.3. And this is the beam cross section. It's a rectangular beam with a width of 20 and height of 30 centimeter. So let's go to Abaqus. The first thing we're going to do, we create the geometry of the beam. Click on create part. Select 2D planar deformable wire. As the approximate size, I'm going to use 25. I call the part and name beam. So continue and click on create lines, and I'm going to create an approximate sketch for the geometry, and then I fix the dimensions. So our beam has 3 segments, and the length of the first segment is 5 meters. So as you can see, if I click on here, add dimensions, and add a dimension constraint to the first segment and put the length equal to 5, Abaqus adjusts the length of the first segment to be 5, and the length of the second segment is 4 meters, and the last segment is 7 meters. So we're going to do the same thing. Click on add dimensions. Click on add dimensions, select the second segment, and we're going to put 4 here, and the last piece is 7 meters. So we define 7 meters for the last piece. So this is the geometry of the beam. Click on done, and that's it. Now, after defining the part, we go to property, click on create material. Our material is steel, and we have an elastic material. So under mechanical elasticity elastic, we define the Young's modulus to be 200 gigapascal. The units that I'm going to use here are going to be kilonewton for force and meter for length. So the unit of Young's modulus by Abaqus is going to be kilopascal. So 200 gigapascal is going to be 200E6 kilopascal. And Poisson's ratio is 0.3. So we divide, click on OK. After that, we need to create section 1. Again, I call it a beam. And category is beam, type is beam, continue. We need to define a profile for the beam. Basically, we need to define the cross section of the beam here. So click on create profile, and for the profile, our cross section is rectangular. So I'm selecting as the name as rectangular, and the shape is rectangular. Okay, so click on rectangular, select rectangular as the shape, and the width of the beam is 20 centimeters, so it's 0.2 meters, and the height is 0.3 or 30 centimeters. So basically, this is the width and this is the height. So if I click on OK, and the material that we have is steel, it's automatically selected because that's the only kind of material that we have, and then click OK. The third part is to assign the section to the beam. So click on assign section and select the whole beam and click done. And the section that we have is the beam section that we just defined, and click OK. Now the last part in defining the beam property is to define the orientations of the 3 axes. So click on assign beam orientation, select the whole beam, and the arrows you see are the tangential directions, and we need to enter the direction, the N1 direction. So basically the direction for the direction of the neutral axis of the beam. So this is the default, is correct for our problem, so we don't need to change anything. So just press enter, and you can see the three axes T, N1 and N2, and they are correct. So click on OK. Done. So now if you want to see the beam cross section, click on View, Part Display option, General, and Render Beam Profile, and click OK. If you rotate the beam, you can see the cross section of the beam. So you can see that this is a rectangular cross section. You could have defined other kind of cross sections for the beam, like eye-shaped beams, boxes. Yeah, there are many different options, circulars. So this is what we wanted. So we move forward to the assembly. We bring an instance of the beam that we created, and we bring it as a dependent instance to the assembly. And the next part is to define a step. So if you go to the step module, click on create a step, and I don't change the name. This is a step 1. You can change it if you want. You can change the name of the step, and the step type is static, so the default is good. Continue, and all the default values here are fine. So we just click on OK. We go to the field output manager to see what kind of output we have and to see if we want more outputs. So these are the outputs that are printed by Abaqus. I think you may want to add SF also, section forces and moments to this. I think that's I think these are all that we need for now. So click OK and dismiss. Then we can go to load, and we can, let's just start with the boundary conditions. So click on create boundary conditions or the supports. Let's just start with the fixed support, and type is displacement rotation. Click continue and click on this point. So basically select this point and click done, and we want all the 3 degrees of freedom to be fixed. So click OK. So basically this is what we are doing. We fixed this end. Now we have 2 rollers also, so we need to define those rollers as well. So let's go to the boundary conditions, rollers, and displacement rotation. Click here, and then we're going to select these 2 points. So I'm going to select the first one by clicking on it. To select the second one, I hold the shift button down, and then I click on the second one. So both of them are selected now. Done. And the rollers, only the displacement in the Y direction is fixed. So this is what we have as the boundary conditions. Now we need to apply the forces. Click on create load. The first one is a 10 kilonewton load, so I call it load 10. And the type of the load that I'm going to select is a line load. So click on line load and continue. And the first load is applied to this segment. So we select this piece, done. And the component is in 10 kilonewton downward, so we put negative 10. We do the same thing for the second part. Load, I call it load 15. And it's a line load again. Select the second piece. done, and -15. All right, so all the loads are defined. We go to mesh. We define the size of the mesh or the size of the elements. If I click on seed edges, I get this error message. The reason for this is that our instance is a dependent instance, so we have to mesh the part, we cannot mesh the assembly. So if I dismiss this, and here instead of assembly I choose part, now I can mesh it. So if I click on this and then I see this, I say that the size of the elements, I want the size of the elements to be 0.5. Click OK. If I turn off the render or the profile, then I can see the seed points here. And the second part is to assign element type. So click on assign element type here, select the whole beam, and basically for beam you can choose linear or quadratic. For this problem I go with linear, but you can select quadratic as well. So quadratic beams have 3 nodes. So if I click here, it explains a 3-node quadratic beam in a plane. So let's go with linear elements, which are 2-node linear beam elements. Okay, and now we mesh it. Mesh the part, select the whole beam. Actually it says okay to mesh the part, yes, and the beam is meshed. To see the nodes, go to view, part display option, mesh, show element and node labels, and here you can see the elements and node labels. So we have 33 nodes and 32 elements. Let's bring everything to the XY plane. So now we can create a job. Go to the job module, create job. I'll call it beam overhang, and I added 1 at the end also. Continue and okay. And if you go to the tree on the right click on the job that you just created and click on submit to submit the job for the analysis. And it should take about a minute to finish. So it's running now. You can monitor the progress for this simple job. There is only 1 step, so it's already done actually. So click on the job, right click on the job, and click on results. Alright, so these are the results. We can see the deformation of the beam. So if I click on this contour here, click U and the displacements, here you can see the deformed shape of the beam and the magnitude of the deformations. So the maximum magnitude is about 8 centimeter downward. We can see the beam stresses. So for beam stresses, one thing to have in mind is that in here, in the visualization part, you need to go to the ODB display options and make sure that render beam profile is on. If it's not on, then you're going to get an error. Okay, so if, for example, if I go over the displacement and I turn this off, and then I decide to see the beam stress, I'm going to get an error. Okay, so we must turn the render beam profile option on to be able to see the beam stresses. So the component of the stress that we want to see is S11. So you can see the stresses. You can see that the maximum stress here is happening in this cross section of the beam. The top part is in tension, the bottom part is in compression. The maximum tension is about it's not that big, it's less than 1 megapascal actually. So this is the stress distribution in this beam. We can create a report. Let's go to the report, field output, and let's say we want unique normal, unique nodal. Let's say we want to get the support reactions. So I choose the reaction forces and the reaction moments, and I'm going to select overhang reactions. This is the name of the file that the report is going to be written to. Okay, and if we go to the working directory, if you look at this, these are the reactions of the nodes. So RF1, RF2, and RM. The reaction, the X, Y, and the bending moment. So you can see that the first node has a 0 reaction in the X direction, a 25 kilonewton reaction in the Y, and a bending moment of 41.5 kilonewton meter. And you can see the same thing, this the support reactions for the rollers also. One of them is negative 117, the other one is 237. So that's it for today. You can get a report for other things as well. Like if you want to get a report on the stress or displacement, basically you do the same thing as well as I showed you here. Thank you.